Okay.
Yeah, so thank you so much, Giovanni, for coming along and presenting for us today, and thank you for everyone who's listening. So today our webinar is titled by Climate Change, Extreme Wildfires and Air Pollution. Our presenter today is Dr. Giovanni from University of New South Wales. He's a postdoctoral researcher at the Climate Change Center at the University of NSW. Giovanni has keen interest in air pollution metrology and has worked in projects investigating the impacts of wildfires and prescribed the burning on urban air quality in Sydney. His current research focus is on regional climate modeling, and he has a keen interest in model evaluation, climate change adaptation, and projections of future extreme wildfire risk. Thank you so much, Giovanni, for being with us today. We're looking forward to hear you talk. So just on the side note, we're going to have around 40-45 minutes presentation with Giovanni. Our participants are more than welcome to type their questions in the chat console for us. And it will be great if you mute yourself on entry just for the recording purpose. And we're recording the seminar today, and it will be uploaded on our website later next week. Thank you so much, and thank you, Giovanni. You have the mic.
Thank you very much, Mona, for that introduction, and thank you to you all for coming today and for giving me the opportunity to present some of the research I've been doing of late. So as Mona said, it's various topics that are interrelated: climate change, extreme wildfires, and air pollution. So an overview of the seminar, essentially it's going to be split into two components, two separate streams of research that are nonetheless related. Part one is about air pollution meteorology research. Specifically, when hazard reduction burns are being conducted to mitigate the risk of wildfires, how do they impact air quality in the Sydney urban environment? And how does the meteorology concurrent with those burns actually mediate the effects of the pollution? And we're going to use a statistical modeling approach to explore the relationships between the meteorology and air quality during these burns, and in particular to look at how we can change the scheduling of burns in light of these relationships. Part two is going to look at the increased risks of extreme wildfires in a changing climate. So essentially we want to know, do the conditions that we know or suspect are associated with extreme wildfire development become more common in the future? And then if they do, what are the implications for the occurrences of these extreme dangerous wildfires? What are the implications for us as well as a society? For example, where will those increased risks manifest? What are the implications for policy? Okay, so without further ado, I'll move into part one, meteorological controls on atmospheric particulate pollution during burns. So, as you'll all be aware, Australia suffers from very severe wildfires from time to time. Now, unfortunately, these lead to loss of life sometimes, property damage, and the very large, dangerous wildfires can be very difficult and expensive to control. So hazard reduction burns are one of the mitigation measures to try to reduce the risk of these wildfires occurring or reduce their severity, essentially just burning away the fuel load so that there's less fuel for them to burn. At this point, it's really important to emphasize that this study is not a critique of the viability or efficacy of hazard reduction burns. It's just looking at how they might be managed a bit differently to minimize their impacts on air quality in a very heavily populated area. And talking of heavily populated areas, this is a photo of Sydney city centre taken from the very top of the building that I'm sitting in now in UNSW campus in Kensington, Sydney. It's an automated weather station we've got up there, and it takes photos every 30 seconds, automated. It's not the best quality photo in the world, but you can clearly see Sydney CBD in the distance there. You can see Rowett Racecourse just in the foreground. Overall, a nice, clear, sunny day. And this is the morning of May the 6th, 2016. This is the very next morning, May the 7th, 2016. You can see the city is completely enveloped with a lot of smoke. Very hard to see anything, very, very poor visibility. This is a day when a lot of people are suffering from respiratory issues rising from the smoke. Now, this smoke was from hazard reduction burns that were happening to the west of the CBD out towards the Blue Mountains. So clearly there can be a problem sometimes when these burns occur, and the meteorology today and perhaps some characteristics of the burns coincide to create this sort of problem. So what are the aims then? Well, we first of all want to assess the influence of these burns on air quality in Sydney. And by that, I just mean get a handle from a qualitative perspective, how they might be impacting the air quality. Our target pollutant is PM2.5, which I'm sure you're all familiar with, primarily because of the health impacts of PM2.5, which are now pretty well documented. But the key thing is to understand or improve our understanding of how meteorology influences air quality during the hazard reduction burns. And that's with the ultimate practical aim of helping to improve the decision-making process for scheduling these burns in order to reduce the potential impacts they might have in populated areas. Our study domain is pretty much the entire Sydney Basin, as you can see from this map. And we used only observational data for this study. There was no modeling as such. The 4 triangles that you can see spread from Richmond up in the northwest to Liverpool, Chullora and Elwood in the city are the state government monitoring sites that collect hourly data on key pollutants like PM2.5 and also meteorology data. It's actually a very handy data set, very, very useful, high quality. We also use some data from the Bureau of Meteorology shown by the blue triangles there, mainly rainfall. And also actually Sydney Airport collects a lot of very useful meteorological data for this sort of health impacts study. I should point out as well that the state government has really expanded its air quality network of late. So there are many more sensors now spread across the Sydney environment, which is pretty handy. Now, before we get into the statistical analyses, pulling apart the relationships between covariates, I just want to set the context by looking at the spatiotemporal patterns of hazard reduction burns in Sydney, because it's very much a spatiotemporal problem that we're looking at. And this map, this heat map, shows you the locations of the most frequent, largest and most intense prescribed burns that have happened in Sydney. So the warmer colors show you where most of the large burns tend to happen most frequently. And you can see that very much it's a western and northwestern northerly issue, with these being the locations where the burns tend to happen, much less so towards the northeast or to the south of Sydney. So that's very important to consider when we're going to be interpreting some of the statistical results in a little while. Very much the location signal in the problem space. Of course, there's a strong time signal as well in the underlying data. And this chart shows you the monthly frequencies of hazard reduction burn days. We're looking at all years 2004 to 2016, so a good long period. And you can clearly see there that most hazard reduction burns tend to happen in the autumn months. They completely drop down in the winter and they start to pick up again into late winter, early spring, and then they stop. And the reason for that is, as you'd expect, summer months, late spring is when we get most of the wildfires. So obviously hazard reduction burning shouldn't happen then. Also to consider the potential impacts of hazard reduction burns on air quality. This is the mean PM2.5 monthly concentrations at the 4 stations I mentioned, Chullora, Elwood, Liverpool, Richmond. And just consider that temporal pattern of hazard reduction burning I just showed you. You can really see that starting January, February, not much is going on, but we get into March, along the x-axis there, suddenly the concentration of the mean monthly concentration really starts to pick up, and going right into the end of autumn, and then it starts to drop down again as we go into winter, when we know that there aren't any hazard reduction burns. Personally, I found that quite surprising because just anecdotally, there's a lot of wood-fired heating in Sydney when I'm walking around, which can be another pollutant source. But you can see that going into winter, there's not, the monthly concentration goes right down. And then as we come into the end of winter, into August and early spring, it starts to pick up again. That's kind of interesting, that sort of qualitative signal coming out there. I guess looking at it from a slightly different angle, this is PM2.5 air quality index values. Again, looking at averaging across the 4 sites, and essentially just looking at how the average values vary as a function of different event types. So the blue box plots are when we have no fires of any nature whatsoever. The red box plots are when we have hazard reduction burns only and no other concurrent fires that we know about. Orange ones are wildfires only and no concurrent hazard reduction burns. And the yellow ones are hazard reduction burns and wildfires. And it's very clear, the signal there, the trend. When we have no fires at all, on average, the PM2.5 AQI is lower. And as you might expect, when we have burns or wildfires, on average, it's higher. And of course, if we've got hazard reduction burns and wildfires happening together, then the air quality is at its worst. So it's interesting to see these qualitative signals coming out here just from some basic visualization. Okay, so what exactly is driving the air quality problem other than the burns themselves? So we have a lot of meteorology variables that we can include in the modeling. We had to try and minimize the complexity somehow and pick only a subset of these variables. So we did some exploratory analyses, again, very basic stuff, just visualizing the patterns, just descriptive statistics essentially, to pick out what are the key predictors we're going to use in our modeling approach and look at what influence they might be having on the air quality. And we just had a simple paradigm where we have hazard reduction burn days when PM2.5 is either high or low. So we're only looking at hazard reduction burn days, and we're just splitting the condition into two: burn days, bad pollution; burn days, good air quality. And then looking at how the variables vary as a function of this. And we're looking at the monitoring sites again. You can clearly see that on average, the planetary boundary layer height is always much lower on days when we have burns and poor air quality relative to burns and good air quality. Now, the planetary boundary layer height is essentially the lowest layer of the atmosphere, in which there can be a lot of mixing, a lot of turbulence, and a lot of exchange between that layer and the upper atmosphere. So essentially, the higher the planetary boundary layer, the more dilution of pollutants can occur. So it's clearly a very important factor to consider when we're doing these burns, the planetary boundary layer height. But also fairly basic variables like surface temperature. Again, here you can see that surface temperatures are always a bit cooler when we have burns and high pollution relative to burns and low pollution. And I guess that might not be that surprising. Probably operationally, the burns are going to be happening when it's a bit cooler. However, it's interesting to note that when we look at 24-hour maximum surface temperatures, that pattern reverses. When we have burns and poor air quality, the maximum temperature tends to be higher. So it completely switches. It's kind of interesting. Okay, so that's just to give you a taste of the sort of exploratory analyses we did to pick out some of the important variables we're going to use. Now, to actually look at the relationships between the covariates, to actually model what's happening, we use generalized additive mixed models, GAMS, to look at the relationship between the variables. And that's because a lot of the relationships are strongly nonlinear, and we also have very strong temporal autocorrelation and data that we have to account for, so we don't get an inflated significance in the model. And again, for burn days, we just compared meteorology for high versus low PM2.5. That's essentially how we're conditioning the data. So it's a burn day, we know it's happening, we know there's no other wildfires, we have low PM2.5. What is the meteorology like? And what are the burn characteristics like when we have this situation versus days when we know there are hazard reduction burns and we know there aren't wildfires, yet we end up with that really bad pollution. Again, what has changed in the burns and all the meteorology to end up with this bad air quality scenario? So the main predictive variables, as I've said, are meteorological mainly, and we use a subset. This is just to give you a flavor of some of the variables that we used. We have the planetary boundary layer height again, which I explained earlier. All observational data from the government network and Bureau of Meteorology. Of course, we also looked at the burn characteristics themselves, how often the burns happen, what's their area, distance from the CBD, their duration, so on and so forth. And of course, we've had to look as well at temporal variables. What is the season? When is the burn actually occurring? What is the temporal signal there that is going on? Okay, so I'm just going to give you a flavor of the results. Again, the aim here is to pick out what are the statistically significant relationships and where can we see a very clear distinction in the influence the meteorology is having on the pollution between the two pollution cases. We want to see a difference in how they're influencing pollution on the low pollution case versus the high pollution case. So here we've got the planetary boundary layer height again along the x-axis plotted against PM2.5 concentration. And you can really see a difference between the two pollution conditions and the behavior of the PBLH. You've got this very strong negative relationship when we've got high pollution days, really, really quite clear. Conversely, in a low pollution, it's quite a flat relationship, no real strong association for most of the behavior of the PBLH, just slightly negative when we get to high altitude planetary boundary layer height. So very clear distinction there, and that's what we want to see, to focus on this variable as something that we can potentially use to help schedule these burns. Similarly, temperature, again, a very different set of behaviors between the two pollution conditions. When we have hazard reduction burns and we have high PM2.5, you can see a curvilinear relationship there. It's negative until we get to about 20 degrees, at which point it peters out and then turns into a positive relationship. And again, on low pollution days, not really much of an association there. Wind direction, quite an interesting one. If you look at Elwood over there to the top right, you can see a real like peak there in the curve at about 300 degrees. And that's an orientation of about northwesterly direction. And as we saw, that's where a lot of the hazard reduction burns tend to happen, or a lot of larger ones. But also when we look at the wind behavior in Elwood as a location, it tends to be on the receiving end of northwesterly flows anyway, on average. So it's quite interesting to consider when the burns are happening, whether this sort of information could be taken into account. Cloud cover is kind of an interesting one, because as I've mentioned, we want to try and pick apart differences in the influence of the variables between the low and high pollution conditions. Here you can see that really across the board, it's a negative influence. So there's not really very much difference here that we can see, at least visually, in the influence of cloud cover. And I guess as you can see with higher levels of cloud cover, the PM2.5 is lower. I guess operationally as well, that fire agency is less likely to conduct a burn when it's very cloudy, higher chance of rain, so on and so forth. Okay, so that whole task was with the objective of picking out what are the statistically significant variables, and then how does their behavior vary between burn days and low PM2.5 and burn days and high PM2.5. And this shows you the mean diurnal variation of those key variables during low versus high PM2.5 on burn days only. And if we take PBLH, planetary boundary layer height, up in the top left corner there, you can see very clear distinction. Its magnitude, its height is always lower at the start, early morning, and at the end of the day, relative to burn days of low PM2.5. It's always a couple of 100 meters lower in the early hours of the morning relative to burn days of low PM2.5. And that's really important, because that means that low planetary boundary layer height is trapping the pollutants near to the surface and impeding their dispersal. It's going to make that pollution stick around for a very long time. It will also interact with some of the topographic drainage flows of cold air that we get from the western part of Sydney down into the main area, where you get these cold drainage flows at night, and that will interact with that low planetary boundary layer height to trap the smoke and prevent it dispersing for a long period of time. However, when we get to mid-morning at about 8 o'clock, 9 o'clock onwards and into the afternoon, you can see there's very little difference there in the height of the planetary boundary layer between the high and low pollution conditions. And then as we move into the end of the day, we get this difference again. Similarly, if we look at temperature, down the bottom left there, temperature is always cooler in the early hours of the morning before people go to work, when we have high pollution and burns relative to burns and low pollution. But interestingly here, the relationship switches. When we get to the middle of the day, the temperature is actually higher for the high pollution condition. But the point of all this is to pick out how these variables change their behavior or influence on the pollution as a function of the time of day. So to sum up, we've seen the diurnal variation of the planetary boundary layer heights, cloud cover, temperature, and wind speed have strong influences on PM2.5 concentrations during hazard reduction burns. And the critical take-home message is these factors are always more variable and higher in magnitude during the mornings and evenings of hazard reduction burn days when PM2.5 remains low. And that's kind of a nice finding, because all else being equal, and I realize there are other complexities and considerations to take into account here, but that shows how the timing of hazard reduction burns might be altered to reduce their air quality impacts. is it possible to delay the start of a hazard reduction burn by 1, 2, 3 hours? Because as we've seen, if it can be maybe delayed a little bit later, the planetary boundary layer height, the temperature, the other variables all change and potentially will reduce the air quality impacts of these burns. Now we have further analysis planned here. We want to apply a simulation approach. I'm doing a lot of climate modeling at the moment, so there's a clear crossover here, as you'll see also from the next part of the research. So it would be good to try and wind in some actual simulation because that gives us a bit more control over all the various covariates. And if you'd like to learn more about this particular study, it's been published in Atmospheric Chemistry and Physics. Okay, going to move on to the second part of the research now, which is a little bit different, but perhaps still related. We're looking at how climate change increases the potential for extreme wildfires in southeastern Australia. Now, the particular sort of extreme wildfire that I'm talking about is a pyrocumulonimbus fire. Now, they are a particularly extreme manifestation of a wildfire. You can see an example of one in the image there on the left. That's actually the Cranston pyrocumulonimbus wildfire, or PyroCB, that happened in California last year, actually. So the extreme manifestations of wildfires, you get these very imposing, massive smoke plumes stretching right up into the lower troposphere. And that's because PyroCBs involve a coupling between the fire and the atmosphere. And that coupling drives very, very dangerous, unusual fire conditions. So we really don't want to be near any of these fires. And we certainly would like to have an idea of when or where they might occur so that we might prepare for them. Now, as I mentioned, in California, we've had recent cases of these fires. Unfortunately, very, very devastating, caused a lot of fatalities and $24 billion of damage. Now, there's some evidence that climate change is going to amplify the conditions associated with hazard reduction burns. Sorry, not hazard reduction burns, PyroCB development, getting mixed up there. And there's also a risk that the continued urbanization of fire-prone landscapes is going to increase exposure to these events and hence the associated risks. So we really want to understand, if climate change is going to amplify the conditions associated with PyroCB development, how will it do so? And when and where will it do so? This can give you a brief background on pyrocumulonimbus or PyroCB development, because even up to a year ago, they were pretty much new to me. I didn't really know much about them. So it's been an interesting learning experience. Now, PyroCB clouds form when we get a very, very intense, fast burning wildfire. It's often referred to as a blow-up event because it burns a lot of fuel very, very quickly in quite an aerial sort of formation. It's not like a linear burn. And the intense heat from that fire causes the air to rise quite rapidly in the smoke plume. Now that rising turbulent air draws in cooler air at the base of the fire, and that cools the plume. And as that plume rises, the lower atmospheric pressure, the higher it goes, causes the plume air to expand, it cools, and the moisture condenses into cloud. Now, when the environmental conditions are just right, when we have an unstable atmosphere at an altitude of about 1.8 kilometers, pyrocumulonimbus clouds will form, the PyroCB clouds will form. And that's kind of interesting because during their ascent, as those clouds continue to rise, as the plume air cools even more, you can actually get ice and strong winds forming. And that's really interesting because at this point, the fire even starts to develop its own weather patterns. And so, for example, you can get the occurrence of dry lightning. That is lightning without rain. And this is very, very dangerous. It's one of the reasons why these fires can be so deadly, because that dry lightning can then ignite another fire tens of kilometers away, up to about 100 kilometers, we think. Also, as this process continues, eventually rain can develop. And when it falls on that very hot, dry air, it actually produces a downburst of very hot, dry air. And as you can imagine, when that hot, dry air hits the fire, then it really blows up and just continues in this sort of cyclical process. And this is one of the things that, as I've understood, not that I have direct experience of it myself, but one of the things that fire agencies are particularly wary of with regards to these fires, because these sorts of downbursts can really make them very, very fierce and unpredictable. Obviously not things you want to be dealing with if you're trying to suppress a fire. So what are the factors that are conducive to PyroCB development? Well, atmospheric instability and dryness are two factors that in theory are conducive to the development of these fires. And the C. Haynes index is one of the indices that indicates the potential for lower tropospheric instability and dryness to influence these wildfires. And I must say, in theory, because this was something that we were still really trying to pin down when we did this study. Now, the C-Haines index, just to give you a brief overview, it's quite simple, just involves summing the two terms, Ca, which is the stability term, which is just the difference between temperatures at 1.5 and 3 kilometers altitude. And then we have a moisture term, the dew point depression at 1.5 kilometers. So we're looking at these two atmospheric phenomena here, instability and dryness. Now, there's some evidence that C-Haines shows an increasing trend. It's getting higher, it's getting worse during the recent decades. So if it is a conducive factor for these wildfires, then that's quite worrying. And that's one of the things that we wanted to try and pull apart in this study. However, as I'm sure you can imagine, we're not likely to get one of these severe fires if the surface fire weather is not conducive to them. So we also looked at surface fire weather conditions, which we quantified using the Forest Fire Danger Index, which looks at temperature, wind speed, humidity, rainfall, recent rainfall, those sorts of variables. There's also been evidence that large increases in FFDI have occurred over recent decades, and that's partially attributable to the increasing temperatures, of which there is an. So the aims then are really to look at whether high index values of FFDI and C-Haines are necessary for pyro-CB development. And I guess implicit in this aim is also, is one or other more important than the other as a predictor for these pyro-CBs? Is perhaps FFDI more important or more conducive to pyro-CB development than C-Haines, or vice versa? We also really want to understand the relationships between these two indices and the occurrence of these fires. And then once we've pulled apart those relationships and we've had a look at how they work, we want to assess projected changes to the co-occurrences of elevated C-Haines and FFDI values. So when they're both at dangerous levels. And in order to do that future projection, we have to use regional climate models to do that, to project forwards nearly 100 years. And then once we've understood those projected changes and we've understood the relationships between these two quantities and the occurrence of very severe wildfires, finally, what are the implications for any projected changes for the future occurrence of pyro-CBs and also for us as a society? So taking the first part of those aims, looking at the relationships of different wildfire types to C-Haines, FFDI, and landscape ruggedness, essentially, we just want to determine what are the magnitudes of observed C-Haines and FFDI that are coincident with the start dates and locations of historical pyro-CBs. We also want to characterize the landform type upon which the pyro-CBs occurred. And that's because there seems to be some link between the degree of ruggedness of the terrain and the severity of a fire. So for example, when we have a lee slope wind, you can often get a lot of turbulence on that lee slope, a lot of mixing, a lot of interaction between the winds and the surface, which often can make the fire worse. So we really want to see how often pyro-CBs occur on rugged terrain. And obviously, to make this comparison any sense, we have to compare with ordinary wildfires, or that is wildfires that don't exhibit pyrocumulonimbus clouds, they don't exhibit extreme pyroconvection. So we want to compare these two classes of wildfires. We looked at wildfires that we confirmed as pyro-CBs using satellite imagery, Landsat, radar data, and MODIS. And then we looked at standard wildfires, as we called them, which are just simply wildfires that were pretty certain didn't produce pyro-CBs. And look at how they vary. For the regional climate modeling aspect, the future projected changes in C-Haines and FFDI were simulated using regional climate models as part of the NARCLIN project, which produces these projections for a large area of southeastern Australia. That's a partnership between UNSW and several state governments. And we used 3 different regional climate models, where each one has a different set of parameters, just to see how those assumptions vary the outcome. And they're driven by 4 global climate model configurations. Those are models that perform particularly well for southeastern Australia. And essentially, our study domain is the one that's delineated in red there. It's 10 kilometers resolution, and it's nested within the Australasia domain that you can see there. And essentially, we just want to derive C-Haines and FFDI values for 3 20-year periods. We want to look backwards at a historical period to see how things have been, 1990 to 2009, a near future period, 2020 to 2039, and a far future period, which is 2060 to 79. And the key here, the meat of it, is to identify daily instances when both CHAINS and FFDI meet or exceed thresholds that we know conducive to pyrocbs. So we looked at a dangerous threshold, the lower tier of CHAINS greater or equal to 6, FFDI greater or equal to 25, and then a very, very severe tier, higher tier, CHAINS greater or equal to 10, and FFDI greater or equal to 50. To put these numbers in context, CHAINS of 10 is about the 95th percentile of observed CHAINS values over southeastern Australia. 25 FFDI is a very high risk factor for FFDI. FFDI of 50 is severe. That's when we get a total fire ban. So to start pulling apart the relationships between CHAINS, FFDI, landscape ruggedness, and the different fires, essentially here, this illustrates those relationships. The background of this plot is a bivariate histogram, where we show the percentage of grid cell events of different increments of CHAINS and different increments of FFDI. Essentially, we're just showing how often they occur. So if we look there at the bottom left of the plot, you can see the warm colors because lower CHAINS values and lower FFDI values tend to happen more often. As you'd expect, they're less extreme events. And as we go up to the top right of the plot, you can see the colors fading slightly. They're still a bit yellow, but not as common because it's less frequent that we get CHAINS at say 8 and FFDI of about 30. And then obviously when we go up to the far top right of the plot, these very, very extreme values are blue because they're very, very rare. Now superimposed over that background is essentially a scatter plot where we have our observed pyrocbs and standard wildfires. The pyrocbs are in white and the standard wildfires are in red, and they're symbolized in different ways to represent two things. They have a green outline if they occurred over forested terrain, and they have a black outline if they occurred over grassland. And then they're different shapes to represent the degree of ruggedness of the terrain. So essentially, if they're squares, it's flat, plains really is what that represents. And then we have diamonds, crosses, and triangles to represent varying degrees of rugged terrain. Now you can see the white markers are all clustered up the top. Very, very few of them towards the middle or the bottom of the plot. That's because over 3/4 of pyrocbs occur when CHAINS values are very, very, very high. About 80% of them occur when FFDI values are about 25. But as you can see, whilst they cluster towards very high CHAINS values, they actually are spread across a very broad range of FFDI values, which is quite important to consider for later. Now, all but 2 of those pyrocbs occur on rugged landscapes. You can see that only 2 of them are represented as squares. All of the others are crosses and triangles because they really tend to occur only on rugged terrain. If you contrast that with the standard wildfires in red, most of them occur for lower CHAINS values of about 2 to 10 and FFDI of 10 to 40. They really tend to cluster in the lower left part of the plot there. And the vast majority of those standard wildfires are squares because they occur on plains. So we're already seeing a very clear distinction here from this basic visualization. So looking at the results of the modeling, looking forwards, what are the future changes in coincidences of elevated CHAINS and FFDI, looking at spring, so SON. And remember, we've got 2 tiers here. Across the top row, we're going to have CHAINS greater or equal to 6, FFDI greater or equal to 25. Across the bottom, CHAINS greater or equal to 10, FFDI greater or equal to 50. And on the left here, you can see the situation for the historical period. So really the main message here is that days when both of these indices are very high and dangerous are not that common around the populated fringe of southeastern Australia. You're only getting about 5 to 10 days on average per season. So it's not that common. So that's important to look at the context of what I show you next. In the middle there, panels B and E, we have how these indices change in the near future period. So that's 2020 to 2039. And you can see, for example, looking at panel B, there's an increase of about 2, maybe 3 days per season over Victoria, New South Wales, but not really very much is happening. None of those changes are statistically significant. If we look at panel C, here the situation changes. Now we're looking at the far future period, 2060 to 2079. Here you're getting a change of about an increase of about 4 to 5 days on average per season that both sea hanes and FFDI meet these dangerous thresholds. So there's 4 more days, 5 more days on average per season that they're increasing and hitting these dangerous thresholds. And the gray area there, the sort of clouded, stippled gray area, are the locations where that change is statistically significant. And you can see it's significant change across a lot of South Australia, Victoria, Western New South Wales, a little bit of Queensland. And actually that change, that dangerous change is happening over agricultural areas and even near some large urban areas. So kind of interesting there. So a real change. It's almost like a tipping point has been hit. 2020, 2039, not much is happening, but we get to 2060, 2079, and we suddenly get this very, very marked, abrupt change. Now, looking at the more severe criteria along the bottom there, if we look at panel F, you can still see a significant increase in the number of days that both these indices hit dangerous thresholds, but it's much more geographically restricted, but still a problem over parts of Victoria and South Australia. Now that was looking at spring. If we look at summer, DJF, just flicking back and forth, if you look at panel C, you can see that we still have a problem in summer, but it's not nearly as geographically widespread. In panel C there, it's really contained to Victoria and a bit of South Australia, and actually quite near coastal areas. So again, areas where we have a lot of people living. Now, when we actually look at sub-seasonal timescales, try and find the months where we're getting these big dangerous changes, it turns out that nearly all the change is happening in November. You can see up there in panel C, all the significant change is happening again around Victoria, South Australia, a bit of New South Wales, Queensland. And when we compare it with September, October, at panel C there, you can see there's a real clear distinction with most of the change confined to November. And when we look at summer months, it's also very similar. Most of the changes are confined to December. But like I said, there's one clear message I want to pass on here. It's going back to spring now, we're getting this massive significant change in panel C. Looking at DJF in the summer, it's much, much smaller. It really looks like there's a forward extension of the dangerous fire weather into the spring. Okay, so what could be driving those changes? What are the factors linked to projected increases in sea hanes? Well, remember, sea hanes involves summing 2 terms. CA is the stability term, how much atmospheric instability we got. Now, the sea hanes scores increased by a very small amount over most of the region in 2060-79 relative to 1990, 2009. In fact, if you look at panel A there, you can see they decrease in some areas. You're getting a decrease. In contrast, complete contrast, the moisture term, CB, they increased by between 0.2 and 0.5 over most regions during November in 2060-79. And if you see the very red, intense change, it's mainly centered on that area of extreme danger that I just mentioned. So that's kind of interesting. So we're expecting that drier air at about 1.5 kilometers altitude is what is going to be driving this particular change that we just looked at. Okay, to conclusions then. Sea hanes is a better indicator of pyrocb development than FFDI, but as we saw, the landscape ruggedness also plays a role. Now, I think the plot I showed you earlier, the histogram, showed that finding in one way, but if we just look at it another way, just comparing two histograms, we've got sea hanes on the left there. The red bars are the pyrocbs, and you can see they're really clustered up to the higher levels of sea hanes, whereas the standard wildfires are spread across all sorts of values of sea hanes. If we now compare that with FFDI on the right, you can see the red bars representing the pyrocbs are spread across a very broad range of FFDI values. So it looks like sea hanes is a very useful covariate of these dangerous wildfires. Projected coincidences of elevated sea hanes and FFDI increase in frequency, but the increase in frequency predominantly in November, as opposed to all other months. And that's an important finding because the extension of the season conducive to pyrocbs in the spring has a lot of practical ramifications. Well, first of all, Australian pyrocbs are typically summer phenomena, but that change in seasonality also has potential implications for resource allocations by fire agencies, who of course have finite resources to deal with this problem. Those projected changes in sea hanes are primarily associated with increased dryness at an altitude of about 850 hectopascals. And this has relevance to the mitigation of pyrocbs. And I think it also has implications for continued urban expansion on fire-prone landscapes in Australia and elsewhere in the world. We saw the significant increase in dangerous days was happening over a very large area of very populated places in Australia. And these are all regions that are growing at varying rates. So this might be something that we should consider when we're planning urban expansion. So if you'd like to see any more details about that, that study has been published in Geophysical Research Letters. And at this point, I'd like to say thank you very much for listening and also for inviting me to talk with you today. Thank you very much.
Thanks so much. Thanks so much, Giovanni. It was quite interesting talk. And we actually have a couple of questions here from Faye. Can you see it at the chat console on the right side, Giovanni, or you would like me to read it out?
Let's see if I can get it. Maybe if you could read it to me, please.
Yeah, that's sure. No worries. So it's from Faye. So the first question she was asking about what was the definition or the cut point used to divide planned burns associated with good versus poor air quality?
I think that's a good question. It was a while ago that we did that study. I think now from memory, we looked at the mean level of PM 2.5 over quite a long time period. And we defined what is high pollution, low pollution relative to that mean. It's high pollution if it's above the mean. We didn't look at it in any more sophistication on that. Because if you cut the data or manipulate the data too much, it would really start to make the modeling very, very, very difficult. The same sort of results come out if you don't split the pollution conditions in the way I showed you. It's just that splitting them in that way really helped distinguish the behavior of different variables. But that's a good question. And probably if I were to do this study again, I would look at different ways of differentiating between high and poor air quality.
Yeah. Thank you, Giovanni. I have another question actually from Faye. She's asking, to what extent did area burned correlate with PM in hazards reduction burns?
Yeah, that was a surprising result. We didn't get a significant relationship for that. I only showed you a subset of the GAM response curves that we generated. There was a positive association in terms of the influence of area, but it wasn't statistically significant. And so because of that, we discarded it from the final analysis.
Thank you, Giovanni. Faye, if there's anything further, we can go it with Giovanni, but I have another question actually from Jeff. So from Jeff, he's asking about, for the HRB study, did you look at parameters like distance from HRB to monitor a spatial extent of HRB area burned?
Yes, yeah, we looked at those burn characteristics. We looked at distance from the mean geographic center of the monitoring stations. We looked at their area. We looked at how long they burnt. We also looked at their elevation. How high they were, whether they were on hilly terrain. We looked at all those sorts of factors, and the only thing that really seemed to have a significant influence was the distance of the burn from the city. So that seemed to be a factor. That being said, I think that there's a lot of burn type variables that we might want to consider that we couldn't. So for example, the phase of the burn, because it would seem that when the burn is smoldering, that's actually when it emits a lot of the smoke. So that would be quite good to take into account. Also, we were looking at observational data that was recorded by the fire agencies. So they just recorded the day of occurrence of the fires. They couldn't look, they didn't provide the specific hour, the exact time at which they occurred. So there were a lot of burn variables really that would be good to bring into a new analysis.
Actually, I can, if Jeff or Faye would like to use the microphone, I can unmute them and they can discuss further. But I have another question actually from Rachel. So she's asking, is overnight temperature a significant factor?
We just rolled temperature into hourly values for each day. So we didn't look specifically at overnight temperature, but I think that would be a good thing to look at because that might be an important factor with regards to temperature inversions. And also actually other variables that we looked at. Overnight temperature could be a real important influence on the planetary boundary layer height that I mentioned. So that's actually a really good suggestion. Thank you.
Thank you, Giovanni. Jeff, do you like to, I've unmuted Jeff, so do you like to take it further?
Yeah, thanks. I may have missed this, Giovanni. Thanks for the presentation. It was really great.
Thank you.
Hang on, what was I saying? Oh yeah, the factors that were related to the PM concentration, as I recall in your first presentation, was the boundary layer, the temperature, and the wind speed.
Yeah.
So are they fairly highly correlated factors?
Correlated with each other?
Yeah.
They were correlated, but they didn't exceed the threshold that we placed on that. We actually discarded a lot of variables because there was so much covariance.
Right.
So
okay.
we actually only ended up with just under 10 meteorological variables in the end because we had, as you'd expect, all this covariation.
Yes.
That obviously we didn't want in the modelling. So as you'd expect, there is some relation between temperature and the planetary boundary layer height, and even wind speed. But it wasn't too strong to invalidate the modelling.
Right.
Yeah, and this is stuff that, I mean, forgive me for not being able to give you the exact threshold that we used, but it was done with some rigour.
Yeah, sure. Yeah, absolutely. I can imagine. Yeah.
Yeah, it's recorded in the study.
Great. Yeah, I'll have a look. Thank you. Thank you very much for that.
Thanks very much.
Thank you, Jeff. Faye, do you want to have a chat with Giovanni? I'll unmute Faye now.
Oh, hi, Giovanni. I don't have any further questions. I really enjoyed your talk, and I think it's really great, practical, and really helpful research to be doing. So I'll look forward to reading your papers.
Thank you very much, and thank you for the questions. Good stuff.
Thanks so much, Faye. Thank you. It seems like, oh, okay. So do we have any further questions? No, actually, they're just more thank you and great research and great talk. We all really enjoyed it today. Thank you so much, Giovanni. Tom, do you like to add anything? There's anything we can add further today, or?
I think that's fine. Did you have what's the best way for people to get in contact if they have questions later on, Giovanni? We'll
probably in the first instance via email, in the first instance, but yeah, any other way is fine.
Yeah, okay. But obviously they'll be able to Google you if they just revert to the CAR website under resources seminar series. This recording will be posted, and yeah, they can probably find you that way.
Yep, that's another good way. Yeah, but yeah, email is also good. And if you come to USW, of course, by all means, give me a call and we can meet up and have a chat.
Definitely. Yeah, thank you so much, Giovanni. It was really good talk. Thank you so much for coming today, and thanks for everyone that joined us today in the seminar, and it will be uploaded on the website later this week. Thank you so much, Giovanni, and thank you for everyone.
Thank you to everyone. Thanks for inviting me.
Thanks. Bye-bye.
Great question. Thank you.
Bye.
Bye.
Okay, thank you.
Thank you, Joe.